Good afternoon, everyone. I would like to begin by thanking the organizers for all the effort put into this conference. My name is Pablo, and I am presenting modeling interactions of a microbial community through an optimal control approach. Probably most of you are acquainted with optimal tracking and control. Therefore, I will begin with a brief introduction on microbial community and interactions. We will then proceed to an example based on the biological process of nitrification in our reactor, which will allow us to state the main model and equations. I am currently undergoing my third year of PhD at the Laboratory of Biotechnology for the Environment in Narbonne, France. One of the main axes of research is engineered ecosystems and how the community structure might affect their functioning. As such, there's a growing demand for models to integrate the knowledge and available measurements. My thesis tries to address this issue by considering mass and energy flows in microbial systems. Let's take a look at some ideas surrounding microbial communities. A plethora of phenomena have been demonstrated on the ability of microbes to sense, interact, and create responses towards other microbes. Statistical analysis has correlated the community structure to the outcome in a wide range of ecosystems. And to make things even more complicated, the traditional paradigm of ecology driving evolution is being turned upside down as quick evolutionary changes have shown to impact population dynamics. The previous insights were obtained because genetic material measurements have become available in ecosystem studies, particularly in engineered ecosystems. However, we will probably never be able to classify all of Earth's microbial life. Some estimates even go as far as claiming that more microbial species exist than stars in the observable universe. Two challenges arise. In a given ecosystem, we would like to identify the functionality of each member. In the past European Control Conference, I discussed this issue in the case of a chemostat. On this occasion, I will tackle the second challenge, which is to identify the interactions between the members of the community. Let's move then to today's example, including the community dynamics in a chemostat model, an example from nitrification. What is a chemostat? It's a reactor used to study microbial development. The chemostat is fed with a solution containing nutrients where the input flow and output flow are equal. Thus, the same volume of liquid phase remains inside the reactor. An important relationship is called the dilution rate, which is the flow divided by the liquid phase volume. It's the inverse of the hydraulic retention time. We will study the case of nitrification happening in a chemostat system. Nitrification is the process in which ammonium is transformed into nitrite and subsequently into nitrate. This process is usually performed by two main groups of bacteria. The first group, called ammonium oxidizing bacteria, or AOB, transforms ammonium into nitrate. The second group is called nitrite oxidizing bacteria, or NOB, which transforms nitrite into nitrate. Yet, in another example of microbial diversity, a species capable of oxidizing directly ammonium into nitrate have been found under specific environmental conditions. We will focus, however, in the case where nitrification is divided in these two groups, AOB and NOB. We arrive to our model, where the process is schematically represented by the pseudo-stoichiometric equations. S1, S2, and S3 represent ammonium, nitrite, and nitrate, respectively. Yi term corresponds to the yield, which is a coefficient expressing how many moles of biomass are produced per mole of ammonium consumed, in the case of AOB, and how many moles of biomass are produced per mole of nitrite consumed, in the case of NOB. When this process takes place in a chemostat, the situation is described as a system of differential equations called mass balance equations. Xi represents the biomass concentration of each species. X, without subscript, represents the vector containing all Xi in the reactor. S1, S2, and S3 represent the concentration of ammonium, nitrite, and nitrate, respectively. S, without subscript, represents the vector containing S1, S2, and S3. Note how D, the dilution rate, appears in every equation as minus D times the concentration of the corresponding state variable, accounting for the mass leaving the reactor. The term S in the third equation represents the concentration of ammonium entering the reactor. In this case, we're modeling when only ammonium enters the reactor. Mu I are the growth rates of each species, which might depend on other state variables. From a modeling perspective, studying microbial interactions can be seen as studying the dependency of the growth rates on state variables xi. One of the first mathematical models of microbial growth rate was originally motivated by substrate limitation, rendering the well-known Monod expression. Other phenomena have been studied as well, such as substrate inhibition or density dependence. From a mathematical standpoint, attention is drawn to the fact that some of the parameters involved in such expressions might not be identifiable. In the following slide, I propose an approach to model the growth rate taking into account general microbial interactions. We define the interaction function as a positive n-valued function. Then the growth rate of each species is determined by the multiplication of a substrate-dependent expression, Fi, and the interaction function corresponding entry, II. If microbes are not interacting, all entries of the interaction function should be 1, in order to recover the substrate dependency of the growth term. Thus, the interaction function should approach to 1 when concentration of microbes is minimal, since interactions should not occur. We also assume it to be a continuously differentiable function. If we have no a priori idea on the form of such an interaction function, how could we try to reconstruct it from measurements? This is where the optimal control setting appears. Let X-OFs be the measurements of the concentration of each species given by the genetic sequencing. For each species, I define FIS as a substrate-dependent expression given by prior knowledge, and let UI be a control variable multiplying this expression. Define U as the vector containing every UI. Note that U should represent the interaction function evaluated in the trajectory of the system. We want to retrieve the controls which best explain our observations, which is given in the integral cost by the norm of X minus X-OFs. At the same time, we want to add a cost that tries to explain data without any interaction, which is given by the norm of vector U minus a vector containing only ones. This is, as explained before, because when the interaction function value is 1 for every entry, no interactions are taking place. Finally, note that we have imposed bounds on the control. Positivity is for the system to be well posed. You cannot have a negative growth rate, while U bar comes from the biological fact that life cannot grow infinitely fast. This system can be restated as a nonlinear optimal tracking problem. Traditionally, the state of the system is supposed to approach a desired trajectory, which in our case are measurements, X-OFs. The approach of Seaman and Banks was used and a sequence of Riccati equations are obtained. Remember that the Riccati equations give the solution to the linear optimal tracking problem. Seaman and Banks proved that a sequence of non-autonomous Riccati equations approaches the optimal solution of the control problem. However, the obtained solution, as shown in equation U tilde, might not lie in the bounds of the control. We therefore saturate this control as seen in equation UT, so it remains an admissible control for the system. We are well aware that this that this is in most cases suboptimal. However, in the fortunate case where U tilde does not reach the control bounds, we're in the presence of the optimal control. Let's apply this method to synthetic data generated by a particular growth function, and let's see if we can reconstruct it. We take the model structure of Dumont-et where they proposed a growth function composed by a monod function with parameters in the table seen at left, multiplied by a term that accounts for pairwise interactions in a nitrifying chemostat. The pairwise interactions are represented in a matrix, seen at right. Note the particular value of A21 in blue, which represents how the concentration of a species 1 negatively affects a species 2. Now we simulate the model with the previously shown growth rate and an increase in the input ammonium as seen by day 150. We get the following outputs. In the upper right corner, the substrates can be seen through time. In the bottom, from left to right, one can see the AOB and NOB concentrations, respectively. Note that an increase in ammonium on day 150 naturally entails an increase in the AOB community as seen in the graph. Without any interactions, one would expect that if more ammonium, S1, is introduced in the system, more nitrate, S2, would be available for the NOB, and thus we should observe an increase in the NOB concentration. However, the negative interaction of the AOB towards the NOB, which I made you notice in the last slide, makes the NOB community get washed out of the reactor when the AOB concentration increases. Now we will use the AOB and the NOB concentration through time as X-ops for our control problem. We can see that the method is able to reconstruct the total biomass. Now, the blue line represents the tracking results. The red star represents the synthetic data. The method tracks very accurately the AOB biomass. It also tracks accurately the NOB biomass, but to a lesser extent. But more importantly, it's able to describe the substrate by only using the microbial community observations. Now we present the obtained controls in the upper part of the slide, which in this case can be seen they are optimal since they did not reach the imposed bounds. In the lower part, we present the growth rate. The red stars represent the growth rate of the synthetic data, while the blue line is the reconstructed growth rate from the method. And now the case of the NOB. The method is able to reconstruct the substrate pattern and the original growth rate. The choice of matrix Q and R of the norms in the integral cost have an impact on the quality of the feed. Note how the control end value is 1. This is due to the structure of a quadratic regulator with no final cost. In the conference article, we have applied the procedure to real data, and we're able to reconstruct the measured substrate. Probably, as explained in the article, pairwise interactions, as used in the synthetic data, are not able to model correctly the experimental data. Numerically, the control works, but theoretical development for the optimal control is still needed. How to use this reconstruction in the search of an autonomous growth function? An idea would be to create a static optimization problem with the reconstructed growth rate as input and the parameters of a particular expression as optimization variable. This takes us back to an identifiability issue, and we only have partial results on that topic. Thank you for your attention.